Okay, good afternoon again, everyone, and welcome to our first class in the AI for Developers track. So, like I had already said, AI for Developers, as the name implies, it's for developers. It's one of the first things that we are doing in KodeCamp, 5X. I think this one the first time we are doing this kind of a track. I personally have not been part of this kind of training. So it's also a new experience for me, right? And being able to teach it based on all the knowledge I have had and also all the knowledge that I'm also getting, for me, it's a great experience. So AI for developers basically is going to deal with how you as a developer can get the most out of AI. So it's not really about you building AI, it's about you using AI not just as a tool to improve your own productivity as a developer, but also to use it to enhance and enrich the products that you will build as a developer. So having said that, let's just jump into it. So this first slide, I realize that maybe a bunch of people here may not know much about me. So I have put this slide here just to introduce myself. My name is Aniebet Udo. I'm an electrical and electronic engineer from, my background in training. But that was a long time ago. I finished with the first degree in that area, but that was around 2000 or so. So that's 25 years ago. Before then, I had already started off as a software developer, learning how to code on my own. Sometime like 30 something years ago, 32 or 33 years ago. I started much early when I was young. I like training people. I like developing. It's something I like sharing my knowledge. That's something that gives me a lot of a sense of value, a sense of accomplishment. So that's why I'm here, and that's why, something like Code Camp is here. These are the areas of my specialization. I've spent a long time in tech. So over these years, I have definitely accumulated a lot of knowledge in a lot of areas, from control systems engineering, which was my core field. I worked in the oil and gas industry for 18 years before I retired 2 years ago to focus on running Code House and Code Camp. I focus on field instrumentation, control systems. So I have skills in programming PLCs. In fact, anything that has to do with programming. I basically just love programming. So um, it's no surprise that I'm doing anything that has to do with programming. I'm a full stack software developer. So what that means basically is back end, front end, middle end, all the ends, right? Mobile. I built mobile apps long before Google existed, talk less of Android. So in those days, we used to do what we call J2ME, Java 2 Mobile Edition. Symbian, before Symbian even existed, which is the Nokia operating system for mobile. Yeah, so I also do DevOps, system administration, Linux system. I worked as a programmer for 2 years before I got into the oil and gas industry. So that's where I got my Linux system administration skills. I started doing AI and machine learning in 2002 during my youth service. I started learning about neural networks. So that's 23 years ago. And so I've been doing stuff on AI for a long time. Mobile development, programming languages. I don't know if these are all of them, but I tried to write as many as I could remember. Um, PHP, C, C++, C Sharp, Python, Java, Kotlin, Flutter, Swift, JavaScript, Objective-C, Visual Basic. There are probably a bunch of other ones. Frameworks I've used in the past to build software, Drupal, Symfony, Laravel, those are PHP frameworks. Prado Yi, CodeIgniter. Prototype is a JavaScript, jQuery, React, Vue, Node.js, SQLite, Fast API, and a lot of others. TensorFlow, PyTorch, Keras, JAX, those are machine learning frameworks. Then we have embedded systems and IoT. So I also like building electronic devices and all of that, and then DevOps. So that's me in a summary. Okay, so now we go to talk about AI. So I want to start this by taking everyone through AI. We really need to know what AI is. For you to be able to use something, you need to understand that thing. You can't get the best out of something that you do not understand. So while we are not really going to delve deep into it, trying to, train models and things like that, but at least we need to have a very good and clear understanding of what AI looks like. So for today and for this week, that will be where we will be focusing on. Before then, though, I will this is a quick overview of how the course will look like for the entire period of CodeCamp 5X. So we start this week with orientation, and we'll talk about AI in modern software development, basically introduction to AI, what's all of that. Then we'll go into AI assisted development workflows, which is basically how can you as a developer boost your capability, your productivity, right? Using tools. There are tools that will write code for you. There are tools that will review PRs for you. There are tools that will do all sorts of things. But you need to understand the capacity, the capabilities, and the limitations of those tools. If you don't, then you fall into mistakes. So that's what we'll look at next week, week 2. Third week, we'll look at some of the SDKs that are available and APIs are available for you to leverage on as a developer in order to be able to build your tools or your products. Then we are going to also look at integrating AI utilities into your development tools. So things like your IDEs, how do you bring AI into your IDEs for autocomplete, for refactoring and all that kind of stuff. Then after that, we start talking about how you can use these same AI tools and services, not just to improve your own um, throughput and your own productivity, but to enhance the products that you build. So we are going to start looking at how you can work with pre-trained models. So pre-trained models, hosted models, these are models. A model, we'll talk about that shortly, but a model is the thing that exhibits intelligence, in machine learning. So the models are the things that do this intelligent stuff, right? So how do you work with them? Pre-trained are the ones that have been trained for you. So we are not really going to be training models, but we're going to use the ones that have been trained. And then the ones that are hosted. So either you host it yourself or they are hosted by, all of these big AI companies from the likes of OpenAI, the GPTs, Amazon, AWS, XAI, Google, Microsoft, Azure, and, there are a whole lot of them now. So we're going to look at some of those. Then we'll now go into this from a front end, back end standpoint. So we'll start with the back end. As a back-end developer, I believe there are a bunch of us here who are back-end developers. How can you set up these models and provide an API around these models so that you serve like a back-end developer that you are building APIs for others to consume? You now build APIs that are intelligent, that use AI models so that you can serve those APIs. That's week 6. So we are going to look at how you can set them up, deployment, automation, what we call ML ops, AI ops, Git ops, and all of that, right? Then we talk about how to enhance the native capabilities of AI. So first of all, you need to understand what are the native capabilities of AI. What are the strengths and what are the weaknesses of these AI models, right? And once you understand that, then you understand where you as a developer needs to step in to enhance where it is demonstrating weaknesses. Okay. So you hear of things like RAG, which is retrieval augmented generation, where you basically are augmenting the generative capacity of these AI models. Then vector databases, we are going to talk a lot about that because that's very important. Vector database is basically a structure, a data structure that lends itself to um, inference, the kind of inference that AI uses. If you don't organize data in that format, it will not be very effective. So a vector database is a way of you augmenting the knowledge that AI already has with something that is more specific and more domain specific. So I'll talk more about that. Then we'll talk about how you can deploy and scale those AI APIs that you have built still on the back end. Then by the time we get to week 9, we now switch to the front end and we are going to start talking about consuming these AI enabled APIs, SDKs, and capacity that they bring to you. We start with designing. So for those of us who are designers or have some design, inclinations, you are going to learn about modern ways of AI first design, what I call AI first design. In those days, we used to talk about mobile first, responsive first, and all of that. Now we're talking about AI first design. So how do you design in such a way that you leverage on the AI capabilities that we have all around us? And your design shouldn't look like it's some kind of you know, afterthought that you attached. So you should think about AI first, think about ability to prompt your apps and things like that. Then we'll now go into the AI basics with front end. So we're going to use React, JavaScript, and Next.js and build a couple of apps, right? Um, the focus will really be about enriching the apps with AI capabilities. We're going to talk about a specific AI framework called Mastra AI. So that's a TypeScript framework. So any JavaScript project that you have, irrespective of the front end framework, whether it's React, whether it's Next.js, whether it's Vue.js, Angular, whatever, you can use Mastra AI to bring in some AI capability into it. So then we'll go into week 12 where we'll do more advanced stuff with Mastra AI. We're talking about workflows, state management. So there's a whole bunch of stuff involved. Then we now look at attaching it to the back end using what we call backend intelligence with LangChain. So LangChain is also another very powerful framework and tool that allows you to cascade or to chain. That's why it's called LangChain. It allows you to cascade multiple AI workflows or systems in a way that is logical. And then after that, we will talk about integrating Mastra with LangChain. And thereafter, the next time we'll be doing capstone project sometime in week 15 or 16. So that's how the course will look like. Okay, I can see that there's a hand up. So Ginika, you can go ahead with your question.
Okay, thank you very much, sir. Please, I just want to find out, for the front end, those of us that are mobile, this Mastra, can't we work with it on mobile, or all of us have to switch to React?
Well, Mastra is a TypeScript framework, so you can only do it if you are doing JavaScript, whether it's React or Vue or anything else, right? So if you are doing mobile, I guess it's Flutter because so I've actually thought about that. You probably will have to do a bit of the JavaScript, but alternatively, I think we can look for ways for you to implement these things in Flutter. The thing we need to understand is these are more about the principles than the specific code. Yeah, the code helps you to apply the principles and see how it works. So with something like Flutter, we'll have to figure out a way. But you might also have to, that's why I asked that question on the channel, and everybody said let's go in for it. So go in for it, and we'll see how we can use Mastra. It shouldn't be too difficult. Like I said, if you're a programmer, you're a programmer. Okay. So we'll look for ways to carry everybody along. But I'm also interested to see if you can work out ways to apply those same principles in your Flutter code bases. But like I said, it's really about principles, not about specific languages or code that you're writing.
All right, sir. Thank you, sir. I'll just research on it and see what comes up.
Okay,
Thank you,
great.
sir.
So for this week, this is our objective. We are going to just have an overview. Today is really going to be about talking about AI. We're not really going to go into a lot of coding, or in fact, we're not really going to do any coding or anything like that. It's really for everyone to understand what AI is. And I'm not going to make any assumptions about people's background or if you have done AI before or anything. I'm just going to assume we're all starting from a clean slate. The only assumption I'm making is that everyone here has some programming or development, software development experience, right? So we are going to look at AI. We're going to discuss what AI is. We're going to have some historical, look into AI. How did it start? What is it all about? Then we're going to talk about differences between AI, machine learning, deep learning, and all of that. A lot of people don't know the difference. People are still confused. They don't know what's AI, what's ML, what's DL, and all of that. So we'll talk about that. Then after that, we'll talk about what do we have available to us? We'll talk about what it means to be an AI, or what AI for developer means. We'll talk about that as well, and what it means to be an AI engineer, what it means to be an ML engineer. We're going to compare and contrast that as well. Then we are going to look at the things that are available to us as people who want to use AI. What are the tools available? So we'll look at the landscape of it. We'll look at different types of AI systems. We are going to talk about some of them, not in much detail, but enough to have an understanding. What is an LLM? How does it even work? Why does it work? Why does it do all this magic? And therefore, how can I tweak it further? Right? We're going to talk about things like embeddings. What's an embedding? You will need to understand embeddings. If you don't understand embeddings, you will not understand RAG, retrieval augmented um, generation, because essentially it's embeddings, vector databases, and all of that. Vision, speech. How is vision done? How is vision, computer vision done? How is speech recognition done? What's multimodal? When you hear multimodal, what does that even mean? Then we're going to talk about um, what you need to have in place as a developer for us to be able to uh, do the hands-on lessons in this course, where you look at um, things like Node.js, Python, whatever API keys, registering in different AI providers or AI API providers, and all of that. Things like GitHub, Postman, I believe some of us or most of us have experience or some knowledge about that. Then we'll do some hands-on this week, not today, but maybe after the class, we'll look at something that we would do just to get everyone kicked off on it. So that's what we are going to do this week. So let's jump into it. So what is AI? What's artificial intelligence? Artificial intelligence is a field in computer science. It's focused on creating machines or software that can perform tasks that normally you would expect human intelligence to do, right? The other thing you will see is that when we are defining AI, there are two separate definitions. There's a definition that is based on the field of study, and then there's a definition that is based on the products of that field of study. The AI itself, the thing itself that is exhibiting intelligence, we also call it AI, especially in more modern times. But AI in this context also primarily refers to a field of study. And this is some background or history behind it. It was coined, that term AI was coined sometime in 1956. And That's when it started. It was formally recognized as a field of study sometime in the 50s. Then it went through multiple cycles of what we call optimism and disappointment. Has a special name for it. It's called AI winter. And the reason why it's called AI winter is it's very impactful. A lot of things were triggered. So I'll go through that quickly when we are running through the history. So AI has a lot of people tend to think that what we use today, the neural network based models and the AI that is based on neural network, that's the only thing that is AI. But in the past, AI used to be anything that exhibits intelligence. In fact, that's the real definition of AI, right? Artificial intelligence, intelligence that is artificial, is not real, it's not natural. There are two things, it's not real and it's not natural, right? In the past, it used to be both. But these days, the intelligence that neural networks exhibit is not actually fake, it's real, but it's still not natural. So the word still applies, the word artificial still applies. So typically, when you say something is an intelligence, okay, there are certain expectations, there are certain goals that, you know, as AI research, we expect. Learning is one of them. Reasoning is another thing. Knowledge representation. So in AI research, you need to be able to represent knowledge. How do you represent knowledge? What is knowledge in the first place? If knowledge can be what I know your name, you know my name. I know that the sun is up today. I know that the sky is blue, right? I know that sun rises in the east and sets in the west. So this is knowledge, but how do you represent this knowledge? So that's one of the key goals of AI research traditionally in the old days. Planning is another thing, and AI should be able to plan, you know. Then what we call natural language processing or NLP. Natural language processing has always been a goal of AI researchers, being that we want software to be able to understand the way we speak. I don't need to say it in special coded language. I should be able to speak freely, naturally. That's why it's called natural language. And the AI should be able to understand what I'm saying. That used to be a really difficult thing in the past. But of course, over time, that field of natural language processing has grown and developed. We are now taking it for granted that you can actually type a chat in ChatGPT and it understands what you're saying and responds to you. In fact, these days, ChatGPT can even, invent its own language or speak different languages, right? But that used to be a really tough problem at the beginning when AI started as a field. So then there is perception. Perception is your ability to perceive. For humans who have the human natural intelligence, you can see, you can hear, right? You can perceive or sense, smell and all of that. So vision is one of the key areas when you talk of perception, right? In AI. That's why we even have computer vision as part of the tracks that we do here. It's a difficult thing, right? The way images are stored is as a set of pixels, a stream of pixels. But this stream of pixels, how do you make it make sense? How do you interpret it into something? Converting that flat, one-dimensional, two-dimensional stream of pixels into a meaningful, understanding of the world around us. That's computer vision, being able to see shapes, edges, being able to see colors, being able to see motion, to track something that is moving across the screen, you know. Then there's also audio, audio recognition, speech recognition, speech synthesis. So all of that is perception, and then support for robotics. So over the years, AI researchers have continued to adapt and integrate different techniques, wide range of approaches, methodologies, and techniques in order to solve this intelligence problem, this problem of exhibiting intelligence, right? So they've used all kinds of things, starting with search algorithms, using mathematical optimization, approaches, using formal logic, using what we call artificial neural networks, which is something we study in the ML course, right? Um, so many different methods, statistical methods, probabilistic methods, using operations research, economics even, just to be able to demonstrate intelligence. There's even what we call symbolic intelligence, which we'll talk about shortly in the next slide, where we try to represent knowledge using symbols, and then we want to achieve reasoning or logic by manipulating those symbols. And those symbols are manipulated using code. So you're actually writing code, okay? Maybe based on if statements, if this, then that, if this, then that. Those ones are called knowledge-based AI or rule-based AI. So there's such a thing. A lot of people think that AI is only things that learn, right? But there's AI where you actually code it, and some of us here, you may actually have written AI without realizing it. Okay, what we call rule-based or knowledge-based or something, or systems, where you steal your knowledge and you write it as a bunch of rules. So if this, for example, if the if the sun is up, then we'll step out, and so on. So we'll talk about all of that. So there is this thing that we call the task that define intelligence. In other words, in order for you to say that something is intelligent, it has to be able to accomplish a minimum of these tasks, right? One is understanding language, which we just talked about. That's natural language processing, being able to understand natural language as it is, to learn it and understand it without having to, codify that language. By the way, I hope you all know that programming languages, for example, are just codified subset, a very small subset of, human language that's codified and made simple so that we can find it easy to communicate with computers. Without programming languages, we will not be able to communicate with computers. But it has to be very precise. It has to be very specific. You know that if you write code in some languages, maybe like PHP, for example, E language, plus plus, and you forget a semicolon at the end of the line, it's a bug. It fails to run. Sometimes it will tell you that there's a missing semicolon. Sometimes it will not. It will think that you are doing something else, and your code will still run, but it will not run the way you want. So that kind of thing, that was the early stages. Of course, we're still using programming languages now because it is highly efficient. It doesn't make sense to use natural language to program stuff because it takes a lot of cycles to process it. So, but the only thing we could probably do now is use natural language to instruct an AI that will write the code using a programming language that is more efficient. So anyway, that's the first. The second is being able to recognize patterns. So for you to say that an entity is intelligent, whether it's a natural human being or a plant or a software or a robot, it needs to also be able to recognize patterns. So pattern recognition. If you see my face, you know it's my face. If you see your sister or your brother's face, if you see a friend's face, you know it's that person's face, right? You're able to recognize that pattern. You're able to differentiate. So you can see colors, you can differentiate. Another example is medical image analysis. So you can see, two organs and you can tell which one has cancer and the one that doesn't have cancer, right? So a human being or a trained human being, that's a doctor, for example, or a radiographer or whatever, can actually do that, right? So for you to say an intelligence can do that, it needs to be able to, or for you to say that something is intelligent, it needs to be able to do that. So that's the second one. The third one is being able to learn from data. So we do have some kind of AI that, like I said, are knowledge-based, rule-based. You are um, hard coding or coding in the knowledge into it. Those ones cannot learn. But then machine learning is an area of study, a subfield of AI, of artificial intelligence, that focuses on intelligence that can learn, right? That's why it's called machine learning. And that's the main difference. So something that exhibits intelligence should be able to learn from data. Okay. Then making decisions. For example, I have a choice. A game engine is a good example. If you're writing maybe you're programming a game, I might actually think of, giving us that kind of thing. Okay, write an app that can play chess or some other game. Well, chess is already a solved problem, right? Okay, let me not say solved, but um, there's a lot of stuff around chess. But if I gave you a game that, you know, traditionally nobody has written code for it, maybe a Nigerian game. When I was young, I used to want to write an AI for Ayo, this game they call Ayo. I don't know how many of us know that game. If you're Nigerian, you might know that word, but it's a game that has, you carry some, you pick things and distribute them across, some holes, which you can represent with circles. There are now versions of that on the App Store if you check different app stores. But the question is, has anybody even written AI on that? It's something I always wondered. Maybe we can do that here. So being able to um, decide which one to pick, that's one of the key things in writing AI for games. Games is really all about decision making. At each point, which move should I make? It's a choice. And it's not a straightforward choice because each of the choices may have advantage or disadvantage. There might be uncertainty of which one is the best choice. If it was certain, then it's not really a problem. You know which is the best option to take, right? But when there's uncertainty involved, you still have to make the choice. So that's what AI needs to be able to exhibit. Problem solving and planning. So problem solving and planning is I need to also be able to plan. That's where games again come in, like chess, because you can play a move and it looks good, but in the long run, it's bad. For those of us who have some, experience and you have learned chess before. So the question would be, um, how do I know whether this is the best move? Not just for now, but in the future. That's where planning comes in. You do what's called search. Most games actually use search algorithms. Um, one kind of search or the other, Monte Carlo tree search or, minimax search or, tree search algorithms. So there is a data structure we call trees. A game is a typical example of a tree data structure, right? Because a game you start at the beginning of the game, you start in a particular position. The game is set up, you're in a particular position, and you have different moves that you can make. And you have to choose which move you should make that, makes sense, right? So which move makes sense? How do you decide which move is the best move? Sometimes it might be more than one move that is good, but which one is the best? So for games like chess, for checkers or draft or draught, like they call it, you have to think to the next step, not just the current position. You can in the way it's done in programming, right? When you're programming a game engine, is you would look at the first position, you look at all the moves, you go to each move, right? After playing each move, not actually playing it, but searching the game tree, what we call the game tree, you go to one move, you check the position that results from making that move, right? And remember, if it is like a two-player game, then it means it is now your opponent's turn to play. When it's the opponent's turn to play, you have to think of all the moves that the opponent will play and the one that is going to be the best for you and the worst for him or her. Then you from that there can be any number of moves in that position. You choose and you again go down the tree to the next move, which we call depth 3. So if you look at that, let's say we take a game like well any game, but let me just make an assumption. You have a game that um in each position, that game has maybe average of 10 moves per position. So at the starting position, there are 10 possible moves. So from those 10 possible moves, you can have resulting 10 possible positions for the next person to play. In those 10 possible positions, each of them also has 10 possible moves. So you now end up with what? 10 times 10, 100 possible game positions that will arise after the second move has been made. That's 10 raised to power 2. By the time you make the third move, again, each of those 10 raised to power 200 has 10 average 10 possible moves again. So you now have again 100 times 10. That's 1000. That's 10 raised to power 3. So by the time you make you see that it is exponentially increasing, right? From 10 raised to power 1, which is position when you starting position, 10 raised to power 2, the second move, the first move rather, 10 raised to power 3, the third move, right? 10 raised to power 4, fourth move. You can just consider it as 10 raised to power n. So you have a situation where you are saying, by the time you have made, 10 moves, or you have thought ahead 10 moves, there are going to be possibly 10 raised to power 10 possible positions. And there are some games that have much more than that. So you can see that there's an explosion of possibilities or possible moves. The only way to solve that kind of thing is what we call a tree search. You have to go down each of those possibilities. And then when you figure out whether the end position is good or bad, whether it's win or lose, you do what we call back propagation. And that's how you use to determine. So that is a whole other area of study. I'm not going to go into that because that's not the purpose for this. But you can see that chess is a good example where computers, software have demonstrated intelligence. In 1997, a computer program called Deep Blue, well, wasn't just a computer program, it was the entire hardware. It was what we call a mainframe computer that ran the software based on search that was able to beat a human being in chess. By the way, as far as AI is concerned, one of the holy grail was for a computer that can beat a human being. That was achieved in 1997, when Deep Blue beat Garry Kasparov. So this is what AI is. So when you hear intelligence, there are a lot of things behind it. And like I said, I'm not really going to try to get us into the things behind it, but it's good to have an understanding, because when you understand how these things work, you are better able to get the best out of them to optimize how it works. So we have fields of AI. So like I said, AI is broadly divided into two subfields. The one we call symbolic or knowledge-based AI. So these ones are the ones that we call them, uh, you represent the knowledge, you look for a way to represent the knowledge, and you store the knowledge. And in most cases, um, that knowledge is programmed in. The code that you write is actually coding the knowledge in. So you hear of things like knowledge representation, you hear of automated reasoning and planning, you hear of expert system and rule-based systems, you hear of fuzzy logic, soft computing, evolutionary and bio-inspired. So those ones are genetic algorithms. You don't need to go into all of this, but I'm just for information. Then this is where you are programming the knowledge directly. The second broad category is what we call statistical or data-driven AI. This is AI that you do not program the knowledge. You program a framework that allows the AI to gain the knowledge by itself by studying the data that you give to it. That's why it's data driven. You give it information, you give it data, it converts that data into knowledge, right? You train it with that data. That's why it's called machine learning. So any field of AI that is based on data it falls under the field of machine learning. And that's the difference between AI and machine learning. AI is broader. Machine learning is a sub field of AI, of artificial intelligence. Is just one of the approaches to achieving AI, but it is a one and only approach that is based on learning algorithms versus the knowledge-based AI that is not based on learning algorithms, but it's based on algorithms where you, the human being, or the team of developers and experts come together and they distill the knowledge, they represent the knowledge one way or the other, and they program that knowledge into the code base or wherever, the database. Okay, so that's what machine learning is. And there are many different ways of achieving machine learning, right? So if you even dive into machine learning, you'll find that there is I have a slide for that, so I'll just quickly jump to it. Um, we do have different fields of AI. So you see that it looks like there's a lot, and there are actually a lot of them. They are all fields of AI, but some of them refer to AI in terms of what it is used for, right? For example, natural language processing, computer vision, robotics, these refer to use of the AI. We're using it for natural language to understand NLP, computer vision. But when you look at things like machine learning, it's talking about the approach that is used to achieve the AI, machine learning, learning algorithms, expert systems, like I said, rule-based, you program the knowledge. Neural networks and deep learning is an area of machine learning. Now, it is a subfield of machine learning, which is a subfield of AI. So neural networks is just one of the ways that you can implement and realize a learning intelligence. There are many other ways. You also have ways, for example, you have regression systems, you have kernels, support vector mechanisms, you have Bayesian probabilistic methods. There are so many different methods. And since that's not really the purpose of this or the focus of this, I'm not going to go into all of that. But just to let everyone know that when you hear of neural network, a neural network is just one of the ways of achieving a learning, AI. It's one of the subfields of machine learning. So when you hear of deep learning is a subfield of machine learning that is focused on studying and implementing neural networks, basically deep neural networks. So there is what we call deep neural networks and shallow neural networks. But basically, it uses the same principles. So you see fuzzy logic. Fuzzy logic, it's another way of implementing AI. Evolutionary computation is another way of implementing AI. Swarm intelligence, cognitive computing, these are all ways of implementing AI. So these are all different fields. This is another graphic that again talks about the different fields of AI. And and again, we need to be able to differentiate between a field that is referring to how AI is implemented versus a field that is referring to how AI is used. So cognitive computing is a way of implementing AI. Computer vision is a use of AI in computer vision. Machine learning is a way of implementing AI. Neural networks is a way of implementing AI, right? um, Under machine learning. Deep learning is basically a focused study of neural networks, deep neural networks. Natural language processing is a use of AI. So this is again another graphic. See basically the same thing. This one tries to give us some better sub-classification, but you still see the same kind of things here. You see machine learning as a sub-field. Under machine learning, you see deep learning and you see predictive analysis. Predictive analysis is just another approach for you to achieve a learning AI. Then you see speech, which is an application. So text to speech. Text to speech is what we call speech synthesis. In other words, you type in text and what comes out of the AI is speech, right? Speech to text is the reverse, is speech recognition. What you do, you speak to it and it gives you back a text equivalent. So in the old days, before we had all these large language models, what we had was really text to speech, speech to text. So in between, you would have to build some kind of system that will be able to either translate that text or do something in response to that text. As a matter of fact, there was a time I built a banking app that used both text to speech and speech to text. And I used a rule-based system. Now, the rules were given to me by the client who said, okay, we just want to be able to answer a few questions. So there are typical questions that customers go into a bank and ask. Okay, how do I open an account? If I'm opening my account and I have this kind of problem, what do I do? So what did I do? I used, by the way, I use Android. So Android already has a built-in speech-to-text and text-to-speech library. In fact, it's very, very good, excellent libraries they have. I think all the mobile, in fact, almost all languages now have a library that you can use to do, speech synthesis and recognition. Now, so that one wasn't a difficult thing. I didn't need to write that code. Rather, I didn't need to train any models for that. I just used the libraries provided by Android. I know iOS has the same thing. If you're using Flutter, you actually see that it has a similar thing. So all you do is you call a function or a method that is provided by that library, right? You, if it is speech to text, that means it will wait for some input into the microphone, and then you now take that. It's kind of a blob, like a waveform, so it will come as a blob or some other kind of object. You pass it that object as an argument into a function call that will invoke the speech to text engine. The speech to text engine will then give you um speech, sorry, the text equivalent of that speech. Of course, you have to set up the language and everything. So when you do that, you get the text. So what I did now is I get the text. I the part I built was a rule-based logic that will now look at the text and try to analyze that text. By the way, it's not very easy because if the bank tells me when somebody asks, how do I open an account? This is the answer you give the person. The answer part is easy. You just pick the answer, you send it to text to speech, right? The text to speech will generate the speech that corresponds to that answer that you have. But the difficult part is if the bank said something, the rule was something like if somebody asks, how do I open an account? But when people ask, people are not going to ask, how do I open an account? They may not ask exactly in those words, right? You might have written it down as how do I open an account? The person will come and say, I want to open an account. Please, what do I do? You can now see that if you are using simple matching, if this equals to this, that will not work. It's the same question, but the words are different or the order of the words are different. So you need another library, right? That will be able to like do matching. So that one was a headache for me because I had to ask myself, okay, how do I if I wrote what I'm trying to match is how do I open an account, but the person is saying I want to open an account, how do I go about it? If you just say if x equals to y, it will not work because it's not. You need something that understands language. That's where the natural language processing comes in. So I use something we call Watson, um, IBM Watson. IBM Watson, if you go and Google it, this was before the time of ChatGPT. Now it will be very easy now. Just send it to ChatGPT or it's those kind of problems are not problems anymore these days. But in those days, I'm talking about something I did sometime in 2013 or so, right? So there was IBM Watson. They spent a lot of time using this natural language processing method to be able to work out like um if you give it two sentences, it will tell you whether those sentences are similar or whether those two sentences, are asking the same kind of question. There are a lot of features like that. You can go check it out. Just Google IBM Watson, right? So that's what I use. There were a bunch of other service, APIs that provided those services. I can't remember the other one I used. So what I did now is whenever when I've done speech to text, I get that text, I send it to that API, right? Because at the back end of that API, I've set up my rule system to say, okay, if the question is like this, it will classify all whatever text into one of those 5 different types of questions, whether it's about opening an account, whether it's about I lost my password, or whether it's about I want to do what do you call it, biometric, and I want to withdraw money, all those kind of stuff, right? I've set up a smart rule-based system at the back end to do that. So what I then do is when the speech to text gives me the text, I take that text, I send it to that API backend. The API gives me a result that tells me, okay, this text that you sent, it sounds like either question one or question two or question three. That now it's kind of a normalization, right? So I normalize it. So after I normalize it, then I can easily say, okay, this looks like question one. So question one, this is answer one. I now grab answer one, I throw it into the text to speech, and it gives me speech. And this is, you'll find that these are more or less the kind of things you will be doing, right? It was a bit, now it's more powerful. You will be doing more powerful stuff, and we'll talk about some of that. So anyway, um, I'm just kind of giving you an example of something I did. Then we have vision, right? So if you look at this slide, you also see vision, image recognition. It's a whole other area. That's why we even have it as separate thing, computer vision, that Daniel is handling. Then natural language processing. I just talked about that, right? So you can see that that solution I built, where you want an app that people will ask question, and the AI will go to check it out and then respond. You see that I used three different things. I used the text to speech. Sorry, I use speech to text. Then I use natural language processing, which class, remember I just talked about classification. So when it gets the language, it's what we even call sentiment analysis, that you say, okay, this thing that is this text that has come in, does it sound happy or does it sound angry? And they were all of these things. People you really used to be very excited. Ah, man, this thing can detect sentiment and all of that. But the world of today, ChatGPT has killed all of that excitement, because it basically does all of this. And we'll talk about a bit of why when we go to machine learning. So translation is another thing, language translation. You have Google language translation. I hope you know that. Just go to translate.google.com. You can type anything in any language, and you get, the other language that you specified, it will translate for you. One of the things you notice with some of these language translation, especially in the past, is that the translations were not always very accurate, especially for a native speaker of the translation or the language that is translated to. You find if you are a native speaker of both languages, like you understand both languages very well, you put one, what you feel like you see that it's not a very, it's only if you are not a native speaker of one of the languages, then you will not realize that it wasn't a perfect translation. But then that was what was happening then. So another thing is data extraction, which is like, if I am saying something, you want your natural language processing to be able to extract some key data. So still using this bank example, let's say somebody wants to, you know, y- you want to provide the capability for someone to drop complaints or support issues. At the end of the day, no matter what English or local language, whatever the person is speaking, you want to be able to extract some key points. Okay, what is this person complaining about? Is it that they lost their password, or is it this? You want to extract data. So that's another key thing. At the end of the day, what really matters is the data you have extracted. So in those good old days, you write rules to extract. Okay, what's the key data? If the person wants to open an account, I need to extract the account number. Or rather, if the person wants to complain about an issue, I need to extract what is the person's account number, what's the person's phone number, from that conversation. So NLP used to do that as well. Then expert systems, like I said, are systems that you bring an expert. That's why it's called an expert system, right? It's called an expert system because you have an expert or a team of experts who bring their knowledge. Then a developer or a programmer takes that knowledge, comes up with a representation, and then writes the code. The representation of their knowledge is stored either in the code, like a bunch of statements, if then else, and so on, or stored as entries in the database. And this rule-based approach, we still use it today. People went back and revisited because a lot of the old approaches were very weak, but now with LLMs, they have become very useful. So when we talk about RAG later on, retrieval augmented generation, you will realize that it's kind of taking ideas from expert system or rule-based system, because there are some things that an LLM will not be able to do. So what do? You augment, that's why it's called augmented, retrieval augmented generation. Generation is what an LLM does, and we'll talk about that. It generates answers. It is trained to be able to generate. It's basically a GAN, generative adversarial network, or a GPT. GPT, the G in GPT means generate, right? Generative pre-trained transformer. That's what a GPT is. So it generates, words. That's basically what it generates words. But those words, it's following some training that you gave to it. So it's expected to generate something as if it were a human being. That's really what it is, right? I'll talk about that shortly. So, um, so when you use RAG basically is a way of saying, okay, this thing cannot generate stuff exactly the way I would like it to. So I give it some guidance on how to generate answers. That's what it is. We'll talk more about it. So planning, optimization, robotics. So let me move on to the next. Now, yeah, so we are on this slide, and I've really spoken about machine learning already, so I'm not even going to dwell on this. But machine learning is a branch of AI, of artificial intelligence, the field where computers learn patterns from data to make decisions or predictions. The key thing there is predictions without being explicitly programmed with rules. So the main thing is that you are not actually programming the rules, you're not actually programming the knowledge, you're rather programming the framework or the system that allows the AI to learn. And then when it learns, it applies the learning. It uses what it has learned to predict. And it is the prediction that makes AI very powerful these days. So instead of writing logic step by step, we give them examples and it learns the rules, right? So of course, in this box here, you have a more formal definition of machine learning. It's a field of study in artificial intelligence concerned with the development and study of statistical algorithms that can learn from data and generalize to unseen data and thus perform tasks without explicit instructions. So I hope that is a bit more, you know, um, formal language, but it's still the same thing. So the key properties of machine learning: one, it learns from data. We've already said that. Either examples you give it or past experiences. It improves performance over time because over time it sees more data. As it sees more data, it becomes better, it learns more. It works without explicitly coded rules. So you're not coding rules about how it should behave. And then it is used for prediction, classification, and decision making, right? So there are two types of prediction. You can have what we call a regression prediction and you have a classification prediction. A regression prediction is a prediction where you are predicting a specific value. So for example, if you are training a model and you ask it to predict the cost of housing, in Abuja next year, you train it with data on the cost of housing in Abuja in Nigeria for the last 5 or 10 years. When it predicts, it has to give you a specific number, right? But um, classification is more like classification. Who will take first position in the class this year? Is it going to be male or female, right? You give it data on who took first position over the last 10 years, and it will now predict. But when it's predicting, it's not going to predict an exact value. It's going to say that person will be either male or female. So that's how classification is. So this is a very good example, right, of the difference between rule-based and machine learning. The traditional programming, if you wanted to do an email spam filter, right, if that was the task that was given to you, which I might actually give, okay, write an email spam filter to filter spam. So if you wanted to use a rule-based programming, you will do something like, okay, if the email contains the subject of the email or the body of the email contains something like free money, then mark it as spam. But you might find that there will be some times where somebody actually writes, somebody legit, like your auntie that is very rich, writes you an email and says, I have some free money for you. It will now mark it as spam, right? But it's not spam. So sometimes that's the thing with rule-based systems or traditional, rule-based programming. Sometimes you may have situations where the other thing is yeah, you may have situations where the thing doesn't match and there's error. I'm not saying machine learning don't make such errors as well. They do. Um, but the other thing is that this kind of approach, if you send the input that doesn't correspond to anything that you have programmed, it will not know how to handle it, right? Machine learning, on the other hand, you give it thousands of examples of emails and you label the one that is spam and the one that is not spam, right? And by the way, when you are labeling spam and not spam, if you only give it spam email, it still will not learn how to identify, because for a machine learning model, you need to give it positive and negative examples. You need to give all examples of all the things you want it to be able to differentiate. And so it does that. So you give it examples of spam, this one is spam, this one is not spam, and so on. After some time, it is able to learn the pattern of what a spam email looks like and what it learns it on its own, because that's what it's able to do. That's how it's programmed or designed to do. So that's the difference between you writing code normally and you using machine learning. So this is a slide just to, you know, kind of round this off. The machine learning, when you talk about classification of machine learning, you have different ways you can classify it. I think the most common one is you have what we call supervised learning, you have unsupervised learning, right? Then you have semi or self-supervised learning, right? And then you have reinforcement. So basically, those are approaches of training the model or of the model learning. But other ways you can also classify is based on the architecture, how the model is implemented, how the AI is implemented. If you're using neural networks, that's one way. We also call it deep learning. Neural network is actually the approach itself, while deep learning is the study of that approach. Probabilistic methods, Bayesian, you know, theorem and Bayesian probabilistic approaches, tree-based methods using random trees and random forests, right? XGBoost, kernel-based methods using support vector machines and so on, graph-based learning, which is tree search and all of that, then evolutionary methods, genetic algorithms, and so on. So those are all different ways for you to implement AI, you know, under machine learning. And then the last way you could also classify machine learning is based on what the model is actually doing. Is it doing classification? Like I say, classification is you're assigning labels or classes to different things or to the input. Regression is when you are predicting an actual numeric value. Clustering is when you are grouping things that look similar. So clustering is unsupervised, by the way. Anomaly detection is when you want to detect something that's slightly different. A good examples of use of anomaly detection, which what you may be interested in, is in cybersecurity detection of intrusion or viruses or any abnormal behavior in a computing system, right? So how would you detect abnormal behavior in a computing system? You have to take data around not natural behavior of normal behavior of that computing system, whether it's your desktop or a server that you have been asked maybe to write some kind of anomaly detection or intrusion detection. And then you use all of that. It's a model has been trained. You can send that information, and based on the training that it has, it can tell you, hey, this thing doesn't look like what has happened in the last 10 days. Okay, in the last 10 days, the CPU load has been 90%. Then we have a spike to 98%. You know, that's an anomaly. So that's anomaly detection. But if you are just depending on maybe, okay, the CPU percentage, that may not be enough. So that's where AI, especially things like neural networks, really come in, because those can look at multiple parameters instead of just a single parameter. So you could look at the disk usage, how fast the hard drive is spinning, you know, the memory usage, the CPU speed, the CPU temperature, a whole bunch of things. And it looks at all of those things and it can tell you, hey, this thing looks different from what I'm normally used to seeing. That's what anomaly detection is. Then recommendation is recommenders. If you have been to a lot of these e-commerce sites like Amazon, shop, online shop, or Netflix, you know, you see things like, or even the Play stores, you see things like um, the people that watch this movie also watch the other type of movie, or the people that downloaded this app also download these other kinds of app. or the people that bought this thing also bought this other thing. That's recommender. What it's basically doing is it looks at what you have chosen, and it matches that pattern with people who tends to pick the same kind of thing, and then it kind of predicts what you would like based on what those people liked. So that's recommender or recommendation systems. Then you have dimensionality reduction, which is basically multidimensional data that you want to reduce to less dimensions for purpose of visualization and all of that. So these are some of the examples of tasks. Most of these you may not do them, but some of these you may do. A good example is this anomaly detection. That may be something you can even build as a product, right? Recommenders. Okay. So a good example is if incorporating recommenders into your websites or your apps. For example, oh, what would you like to do today kind of thing. Uh-huh. Okay, so I'm going to round up with this section on AI by just talking about concepts and definitions. What is AI? What's ML? I think we've talked about that. This is just a summary slide on that. AI is the umbrella, is the broad field where we study how to make machines exhibit intelligence and perform tasks that normally require human intelligence, right? Which is reasoning, planning, perception, decision making language. Machine learning is a subfield of AI that focuses on systems that learn what they know rather than being programmed by human beings. They learn their knowledge from the data that you give to them, right? So we have examples. Deep learning is a subset of machine learning that focuses on a specific method of accomplishing these learning systems, and that is using neural networks or deep neural networks, right, to learn complex patterns. Reinforcement learning is also a subset of machine learning, but it's based on the approach of training as compared to supervised learning or unsupervised learning. Reinforcement learning is a way of training. You train it by giving it rewards and penalties. You put it in an environment. If it does the right things, you give it positive reward. It does the wrong things, you give it negative rewards or penalties, right? Um, so we'll just go quickly through history of AI. I just have this slide. I think I've summarized it. In 1943 was the beginning of what we call neural networks, when McCulloch and Pitts they proposed a model of an artificial neural network. Sorry, an artificial neuron. By the way, for your information, a neuron that is used in ANNs or artificial neural networks were modeled after the neurons in the brain. I hope you know if you have studied neuroscience or at least done a little bit of neuroscience, you will see that the human brain is actually made up of billions of cells, and those cells are called neurons. And those neurons the brain neurons exhibit some kind of the properties that were kind of distilled or taken out and replicated mathematically. You can actually express this mathematically. It's a mathematical representation, a mathematical model. So the artificial neurons, that model was first proposed by these two um, researchers based on how they study the human brain and the neurons in the brain. So that was 1943, and from there they started. Then Alan Turing in 1950 published Computing Machinery and Intelligence and came up with that thing we call the Turing test. The Turing test basically specifies the things that an intelligence AI can do that would make a human being think it is another human being, basically indistinguishable from another human. So you'll be hearing of this Turing test thing. I'm sure you've heard of it before. It was in 1950. 1956 was when that term artificial intelligence was coined in the Dartmouth workshop, right? We can go do all of this research if you need more information. So that term was coined to represent that field of study, which we now call AI. Then the thing called perceptron was introduced by Rosenblatt in 1958. So a perceptron is basically an implementation of the neuron model. A perceptron is a single neuron, and basically the implementation of it in a computer is what we call a perceptron. So you have a single layer perceptron and you have multi-layer perceptron. And then, well, there were a whole bunch of what we call AI winters and all of that. I'm not going to go into all of that. But then we had back propagation, which was popularized sometime in 1986. So you can see the gap about almost 30 years, right? And eventually, back propagation is the key of how neural networks learn, or any for that matter learns. Because what happens is that you take the difference, what we call the error, between what you are asking the neural network to predict and what is actually predicting. You back propagate it. You use it to adjust what we call the weights. The weights are the places where the knowledge is stored. So you back propagate it, and when you back propagate it into to adjust the weights, it learns. So that is that's what back propagation is. In 1997, Deep Blue beat Gary Kasparov. I've said that already. Um, yeah, Deep Blue was not just software using Minimax, alpha, beta pruning, tree search, right? But it's also hardware that was able to do about 11.9 million flops, floating operations per second. That resulted in maybe about 200 million chess positions. So every second, it could actually examine and go through 200 million chess positions, right? So that is Deep Blue, and well, it was able to beat. The interesting thing is that the chess engines of the world today are many times more powerful than Deep Blue, right? In those days, humans were still competing with, chess engines or with computers, in chess. But now computers have surpassed human beings. So that one is now an old story. Then in 2012, we have what we call AlexNet, which was able to um, achieve a breakthrough in deep learning by there is a benchmark test called ImageNet. ImageNet is basically, first of all, it's an architecture for um, for vision, right? for for recognition, image recognition, and there's a whole bunch of images that is used to make up that benchmark, and there's a certain score. So AlexNet was able to break through the best score at that time. It used neural networks, specifically what we call a convolutional neural network, and then a stacked convolutional neural network is what we call a residual network, and all of that. 2016, we now had something we call AlphaGo, which is a game engine, a successor. Well, it was built by DeepMind. So chess had been conquered in 97. There's this Go. Go is a game that is far more complex than chess because it has far more moves. But computers still were lagging behind human beings. But in 2016, a computer, for the first time in history, a computer defeated a human being, the world champion in Go. And now in Go, the computers are way ahead now. Then in 2017, what we call transformer architecture was introduced. Transformer is a special architecture that was developed that became very efficient in processing, um, you know, information, what we call sequential information. That is information where there is a dependency. For example, in natural language processing, there are things, the meaning of a word depends on the words that come ahead of it or that come before it or come after it, right? So we used to use what we call recurrent neural networks, which were very slow to handle that. Transformers basically boosted that by 1,000. So it was faster to train neural networks to be able to understand language and do all of that sequential stuff, right? And it is really what happened in 2017 that led to ChatGPT. It is Transformer that happened in 2017 that it basically led to the LLMs that we see today, right? Transformers and then GANs. GANs are generative adversarial networks. So and then we have models, generative AI. That was in the 2020s. So we are now in the 2020s, and we are now benefiting from all of these years of research. So check out the timeline. It started in 1943, right? In fact, way behind before that. But um, so these are the key milestones of AI. So that was a good primer. I like to do that so that everyone has a feeling, a sense. This AI we are talking about didn't just fall from the sky. So when someone will come and tell you AI is not magic, right? It isn't magic. People put in sweat and funding. I didn't talk about AI winters and so on. When um all of the hype of AI, when it fails to meet expectations, people lose money, people withdraw investment, and nobody, invests in AI research. What we call AI winters. We had two AI winters, at two different points in time. If you want to get more on this whole thing, you can go watch the video on ML, the machine learning video, because I did the same kind of thing there, but it was in a lot more detail. So AI is not magic. It didn't come from the sky. There are actually well-established techniques and methodologies for achieving the things that AI are achieving today. And there's a lot of compute. In fact, that's one of the things, apart from the transformer architecture, the other thing was computing capacity and what we call GPUs, graphical processing units. These are specially designed to do what we call fast parallel processing, 1,000 times faster than a CPU would do the same thing, right? So that allowed, because training neural networks and inference of neural networks are parallel mathematical operations. One of the most prevalent, in fact, the biggest mathematical operation that happens in neural networks is a matrix multiplication, whether it's a dot or cross multiplication, right? So for those who have done maths and all of that, so GPUs are super, super excellent at doing matrix multiplications really fast. And so with GPUs coming into the fore, that was a thing that just boosted the AI. And so we are in a time in this, in the history of time that um, all of the good things lined up, right? You know, the research, the technologies, the GPU, and boom, we had OpenAI. OpenAI, started sometime in shortly after 20, I can't remember, 17, 18 or so, thereabout, and, focus on research. And now we have what we have. So LLM means a large language model. So it's basically a model. It's why it's called large language model is it's a language model. So it's trained on language data. It's not trained on chess data, for example. It's trained on language data. Basically, all of the you know writings that the world has written. Because the thing is, when it comes to neural networks, neural networks are data heavy. They are data heavy. You need to give neural networks. That's one of the downsides of a neural network compared to classical traditional machine learning approaches. You have to give a lot of data for it to be able to learn and generalize. So if your data is not much, it will overfit or underfit, depending. Well, if the data is not much, it will overfit. If the uh, if the um, if the model is not large enough, it will underfit, right? So, um, yeah, so the internet, I forgot to mention that the internet came to the fore in the year 2000. If for those of you who are old enough, you remember Y2K, right? So the Y2K, the internet boom. So internet brought a lot of data. All of the social media posts that people post, blog posts, all kinds of content became available. So all of this content, what the big companies like Google, OpenAI, and all the rest of them did was they have what we call spiders. A spider is software that basically crawls a website and pulls open. website to public websites because it's public data now. Once you've put it out there, it's public data. So it crawls these websites and it pulls all kinds of text data. That's why it's called language model. It pulls all kinds of text data, and this text data is then used as training data for large models. These models are large in the sense that the size of parameters, you are hearing of things like billions of parameters. A parameter is basically a single floating point number. So by the way, neural networks are basically a bunch of floating point numbers. Now, I'm not going to go into that because maybe if you want to hear about that, we can talk about it in the machine learning class. But it's just a bunch of floating point numbers that have meaning. They actually have meaning. So and training is by adjusting those numbers to for it to be more meaningful. The numbers are meaningful as a whole. That is all the numbers together. The meaning lies in all of the numbers together, not in single numbers. So just think about it like these people that go into the stadium and you see cameras from the top. The people are standing together and they're forming letters or words or characters as a group of people. The characters only come out when you see all of the people. That's why you have to have cameras, all the way from high up in the air. But if you're down and you're looking at one person or two or just a few of them, you will not make out the characters. You will not make out the shapes or characters that they are forming. That's the same principle. It is the number, it is a large number of them in specific positions that make the shape. That's how neural networks are. A single neuron does not make any meaning, but it's when you conglomerate all of them in a particular configuration, that is when it stores knowledge. So, um, a large language model is basically a language model that is huge. 10 billion parameters. If you want to convert that to gigabytes, some of these models are as huge as 1 terabyte. So imagine a model that is bigger than, a terabyte or terabytes, right? And that's what they do. So that's why they're called large language models. They're basically large neural networks that were trained on language data. Okay, so let me round up because I need to get to the point that matters to you who are my audience today. So for you, the developer, artificial intelligence, what is the purpose? What is the value for you, right? So for you as a developer, what does AI mean? What does AI for developer mean, right? Or AI for developers, what does it mean? So first of all, you as a developer, you're not really going to focus on building AI or training AI, right? You are rather going to focus on leveraging it. You as a developer, you should not just focus on building software. You are not just building software. You are building intelligence. You are building intelligent software, but you're not the one building the models that exhibit intelligence. You're just leveraging on the intelligence of those models. You're integrating that intelligence into your application. So in the future, very soon, and that's why some of this course is very important. Very soon, the traditional applications that we have been building will become obsolete. If you just go and build a web app, and I cannot go in there and prompt and get stuff that I want out of it, it will be obsolete. The traditional search bar that you have at the top of websites should be replaced by a prompt where I can just type any free form prompts that I want and I get what I want. This is the mindset change that developers need to have now. And I know some of you just came into KodeCamp and you just learned and you just came out and you were taught the traditional way of doing things. The benefit for you now is that as you have come in here, your mindset, especially as a designer, I don't know how many people are designers here, but designer, developer, your mindset about how you build your apps should change. So the AI for developer means you will use APIs, you use SDKs, you use pre-trained models. Models have been trained by machine learning engineers to enhance your own products, your own software with reasoning, with automation, with personalization. In other words, apps will now have to be reasoning apps. So you need to start thinking about it. And it needs to be AI first. So it is not after you have finished writing your um, folder structure or whatever, then you start thinking, okay, how do I put intelligence? No, Even at the point when you are deciding on your folder structure, you need to ask, where will my prompt button be? Or will it even be a prompt? How will I, you know, fine tune that prompt before I send it to the API? Those are the things. In my website, will I have AI chatbots that can guide people around the site? I want to do this. Okay, click on this to take you here, right? And it's not the traditional chatbots. You know, there are some chatbots that websites that you go now, you go and click the chatbots. There's a chatbot that comes up and you ask it one question and it's giving you another answer. It tells you, oh, this is that. There are no agents on the queue, all kinds of things, right? It needs to be smarter because you have the tools within your grasp now. Recommendation systems, like I just talked about, you should be able to have apps on your website or on your web app or whatever, that if you go there and you need something, it should tell you, okay, if you want this or that, go here, or this is how you can achieve this, or this is where you can get that. Sites that become very friendly, that become conversationally friendly, I can get functionality by conversing with the app. For your information, recently, if you have checked it, OpenAI have released a new browser, and that browser obviously has AI at the back end. So any site that you browse, that AI is there watching. There's also a downside to it, a dark side to it. That AI is there watching and everything. So it will be easy for you to just conversationally talk to that AI and ask it to do stuff based on locations you have visited on your this. Me, I will not download that browser yet, Sha, because AI watching over your shoulders as you are browsing is an interesting thing. But look at that; those are things you can do. Code assistant. Yes, we have Copilot. When GitHub Copilot came out the first time, it was such a big deal, and it was so amazing, right? That was before ChatGPT, by the way. GitHub Copilot came out about a year or so before ChatGPT. And it was amazing that GitHub Copilot could guess the code I want to type and just auto-complete the entire function for me, right? Well, it wasn't entire functions then. It was maybe just like maybe one or two code blocks, right? But then ChatGPT came, and of course, Microsoft and OpenAI, Microsoft now owns OpenAI, and Copilot benefited from that because Copilot belongs to Microsoft as well. GitHub now belongs to Microsoft. So you now have a situation where all of that technology comes together. And now, if you have GitHub Copilot subscription on your VS Code and you go there and you type one or two things, it can basically generate an entire thing for you. Now, that doesn't mean your brain, you should lose your own knowledge or your brain should atrophy, but it does mean that you don't become the servant to the AI, you become the master. But you cannot become a master to an AI if the AI is smarter than you. That is why you cannot, what's the word now? You cannot delegate your intelligence to an AI. You have to become as smarter than the AI. So you become the boss, right? And the AI becomes your pair programmer or your junior developer. And you tell the AI, hey, go do this while I do this. I do the high level planning, you implement. So for example, there are a few people on this, on the WhatsApp, sorry, on the Discord channel that, and it's a good mindset. They said, okay, I, as a developer, I want to do a web app. And that is also my own situation. I don't want to go and start writing HTML, CSS. It's boring. I did HTML, CSS how many years ago? It's boring. So I'll tell ChatGPT, do that for me. I'll give you the design. I can even screen grab the design and give it to ChatGPT. Give me the React template or give me a React component. And it will give you the React component. And you put it in your stuff. Then you write the JavaScript, right? Because that's more complex. So that when I say times 10 your productivity, that is it, right? Imagine you are now sitting down. I used to hate writing HTML, CSS because it takes so much time away from me, right? You have to tweak this, tweak that, but thank God for Tailwind and all the rest. I've actually given that to ChatGPT before. I told it, hey, I screen grabbed a design. Somebody gave me a design and said I should implement it. I implemented our website in 30 minutes. I implemented in 30 minutes, right? So for me to implement in 30 minutes, I screen grabbed it, I gave it to ChatGPT, and it gave me the HTML, CSS. It was plain old. I didn't want to use any frameworks. And then I wrote the JavaScript, and that was it. So you have to be ahead of the AI. Now that's going to be a challenge. Yes, I can see how can you maintain your intelligence. You have to you have to jump ahead of the curve. You have to know what the AI knows. You have to know more than what the AI knows, right? But you have to always what's the word now? Review what the AI does. Don't you know don't delegate your brain to an AI, right? So it's going don't become lazy because the AI is doing it for you. Rather, do more stuff and try to understand every single step as it is going. So that is the future of being a developer. If you don't step into that future, you are going to be out of a job, or you're not even going to get a job if you didn't have in the first place. So that is the mindset. It's a mindset change, right? Open AI. This on this side of this slide, you see a lot of some of the tools are available. I'll look. We'll see more of them in subsequent slides. LLMs, embeddings, we'll talk about embeddings. And embedding is basically a representation of knowledge. Remember, we're talking about knowledge representation, when we're talking about rule-based. Now, um, except that with embeddings, you are not the one that determines the representation. You tell a neural network, you give it data, and the neural network develops its own way of representing that knowledge, right? Those are embeddings, but there are also embeddings that you can craft, but it is going to be a very you know uh tenuous, manual process. It's not something I would like to do. Rather, I would like to train a neural network. It develops embeddings. I extract those embeddings, and I use those embeddings, right? So for language models, for even image generation, APIs, Atropic is the one that gives us Claude. OpenAI gives us the GPTs, right? The generative pre-trained transformers. So you have ChatGPT, which is basically GPT that you use for chat. Now you have what we call multimodal. So the same model is now trained not just to recognize text, but it can also recognize images, right? And videos. That is why, or even sound. That's why you can upload an image into ChatGPT and it will read what is in that image. Because the thing with multimodal is that the same core knowledge, it can reuse it. So you don't even have to retrain it from scratch. As you are training it, it's making there's what we call it's actually there's knowledge embedding. Like this whole knowledge representation, it's actually getting some sense out of what you are training it. So the more you train it on different stuff, the more it's able to connect and create relationships between all of these entities and all of this knowledge. So you also have Hugging Face. Hugging Face provides um, images. It gives you models that it's open. They have a lot of models. It's open. No, I wouldn't say open source, but they are open. Like you can go download their models and use it for image recognition or image generation, right? And all of that. Data sets, inference API. They also have APIs that you can use. Azure has, but those ones are more like enterprise stuff. Okay. So what does being an AI developer mean today, or an AI engineer? We'll talk about that at the end, but look at this. First of all, you need to be able to build AI-enabled features. So you're not expected to invent new models. You should be able to use APIs and SDKs, whatever they are, OpenAI, Azure, Anthropic, and all the rest of them. You should be able to wrap these AI capabilities into your apps, into bots, into workflows, right? Workflows that even take entire, intelligence, tasks that normally human beings would do. That's what we call agents, by the way. And that's why we have agentic AI as well, right? Services. You should be able to convert your AI outputs into usable product features. So the product features, chatbots, writing tools, search. I talked about search before, right? This traditional search thing that we also have at the top of websites. What do you want to turn it into? Can I fully make full use of your website just by typing stuff on the search? Can I access every part of your website, every functionality, just by typing stuff on the search? Automation. So there's a shift in mindset from training models to shipping AI-powered capabilities. Then you need to the developer needs to be able to integrate AI into existing software. So you should know how to plug AI into your back-end services, into your back-end microservices, into your web apps, into your mobile apps. Okay. You should be able to orchestrate, and this is really targeted at people who are back-end developers. You should be able to orchestrate AI calls inside your business logic, right? Not as a separate step or as a separate thing, but inside your business logic, I should be able to pull in intelligence. So if you are writing an ERP or a CRM, right? Can I query, the information in your ERM? For example, if I'm writing an app that does sales and warehouse management, for example, or distribution, should the intelligence not be able to tell me when I'm running out of stock, or should the intelligence not be able to tell me that there is fraud going on somewhere? You understand? Those are some of the things. Securely handling API keys, latency, error handling, retries logging, deploy AI features in CI/CD and production. These are the things that you should be able to do as an AI engineer. You should be able to extend AI using your own developer skills. So this AI exists. They have limitations, right? That's the most important thing that most people don't understand. You see what ChatGPT does. Most people don't realize the amount of work that is done on top of the model. ChatGPT that you're interacting with is not the raw model. If they give you the raw model, you'll see that there are so many things it cannot do. But all of those things are enhanced because you have developers that extend the capability. For example, when you go and ask ChatGPT to do search and give you this or that, how does it search? Does ChatGPT know how to search? No. So there's extensions, right? And that's where things like RAG and so on come in, right? And what we call um, functions also. Well, they still call them functions. So you as a developer, you need to be able to, first of all, prompts that people type, you should be able to fine tune those prompts before you send them to the LLM. Because that's how sometimes in the old days, ChatGPT, you would, there are some questions you ask ChatGPT, it will refuse to answer you, to tell you that it's not allowed to answer those kind of questions. But if you are able to, that's because the front end of ChatGPT, the client, when you type your prompt, that prompt is still fine-tuned by another system prompt, what they call a system prompt. So you have the user prompt and then you have the system prompt. The system prompt fine-tunes the user prompt before it sends it to the model. And then the model takes it and it gives you something that has been modified, you know, in a way. So you need to be able to know how you can do that. And then after the result comes back from the LLM, you also should be able to post-process the output, filter it, restructure the data, validate the data, clean it, and before you display it to the user. Okay, so most of us, all we see is just you type a prompt and you get a response. But when you now become a developer, in the mix of it, you find that there's a whole bunch of other things that you have to do. And then you have to be able to combine the AI results that you get with the search. You should be able to go into the database and pull data. That's where RAGs come in and others. User context, right? Different users will have different user context. Rules, memory, session memory. Because session memory, when you send information to a model doesn't know anything about what people discussed before. It starts from a clean slate. But that will not be a very good user experience. So what people do is you have to first of all create what we call a context, right? That context may involve you sending previous conversations in a sequence. So, and that's really what happens with ChatGPT. Each prompt you send, it is not only that prompt that gets sent. Because if you send a single prompt like that, ChatGPT will not remember the previous conversation and it will just give you as if it's starting afresh, as if it doesn't know you. Think of it like your mother or your father has amnesia, and you went to ask her, okay, that thing that we discussed last week, How far? What do we do? And the person will say, what do we discuss last week? That's what will happen. But because there is context, it can tell you, oh, okay, that thing we discussed, okay, this, that context is actually all of the previous chat. If you go to ChatGPT now, if you have been using it, or Cloud or any of these other LLMs, if you go, you see the whole history, right? That history is sent back again before the one that you just typed, so that it re-establishes the context and allows it to give you an answer that is contextual, that feels like you are continuing the conversation rather than, hey, well, what did we just discuss? You know, so those are some of the things. That's what we mean by user context, rules, and so on. So there's a whole bunch of stuff that's happening behind the scenes under the hood, and we don't even know. Then using tools like function calling. So functions allow you to extend the power and capability of an LLM. So for example, an LLM that doesn't know how to play chess, you now ask it, okay, I want to play chess with you. If I move my bishop to c3, right? What is the next move? The LLM cannot play chess. By the way, LLMs are terrible at chess. But you can create a function where you you are using a real chess engine, and then the LLM knows that it has that function. It knows that if it has to do with chess, it can call this function and send the prompt, or it will translate the prompt and send it. And then the chess function will handle that part and give the response back to the LLM. The LLM gives it to you. That's functions, and that's function calling. So this is how you enhance it in your product, because if somebody types something on your website and says, okay, I want a yellow t-shirt. How many do you have? The LLM doesn't know how many yellow t-shirts you have in your e-commerce site. So the LLM, you have to tell the LLM that it can get that information by calling this function and passing these parameters. And once you do that, then it will, every time you ask it about t-shirts or anything, it will call that function. The function is now a regular function that you write in Python or JavaScript or whatever other language. It will go to the back end, to the database, retrieve it normally as you would normally do, and then you give that information in a particular format to the LLM, and the LLM now responds to the user. So that's functions. Embeddings is also a way you represent the knowledge. Remember, I talked about knowledge representation. So there has to be a way agreed between you and the LLM that the knowledge that it wants to, that you have stored. There's knowledge you can store that the LLM doesn't have. You store in database, like I said, about the stock in your, e-commerce site or whatever, that kind of stuff. So RAG is basically a way to speed up and scale up all of this, right? Retrieval augmented generation. Vector stores is a way to store knowledge in a fast, highly, efficient and highly compatible with LLMs. So the value is in the glue code. You as a developer now are able to write this glue code. If you know what I mean by glue code is like the extra code you have to write in order to implement your own business logic. It doesn't come with the framework, right? So you have a framework like React, and or Next.js, but you still have to write your own little code, to bring everything together. That's glue code. And in the same way, with all of these ones, you also have to write glue code. Constraints and post-processing. So the value of you as a developer is in the API call. Sorry, it's in the glue code that you're writing, these small tweaks that you are doing, not in the API call, because the API call is you are just calling a service. Maybe that you pay some money now to the service and you send them a query, they give you a response. But what you do with it and the pre-processing and the post-processing is what matters. So the other thing is you should be able to treat AI as a software component with constraints. As a developer, you need to understand that models hallucinate. I don't know if you understand what hallucinate means. Hallucination basically is the model, you are asking it questions outside of the what they call out of distribution. That is the training data that it was trained on. It doesn't even have anything close to, you know, what you're asking it. So it will form all kinds of lies and tell you. And you people, if you have used the ChatGPT, you would have seen it. And it's so good at hallucination. If you do not know you will believe what it's telling you. So you need to be able to guard against that. The non-determinism is the second thing. Non-determinism means for the same question, you don't always get the same answer. You get slight variance of the same answer, slight variations. Now, in some situations, it may not really be a bad thing because yeah, you don't want it to be monotonous and always give the same answer. But there are some situations where you always need exactly the same answer for exactly the same question. So in such situations, how do you guard against non-determinism and make sure you're always getting the same deterministic answer? So that's very key. Performance bottlenecks. A lot of people don't think about things like that. Latency, how long it takes for the LLM to process and give you back its answer. What will your user be doing during that time? They'll just be waiting and you'll be giving them a spinning loading icon, right? How do you deal with that? Then there's tokens, token size. LLMs have limit in the length of questions that you can ask them. If it is too long, it breaks down because they have a token size limit. So how do you handle that? Bandwidth, which is a speed, right? There is even things like what do you call it, rate limiting, right? For if it's not a paid thing, they'll rate limit you. If you load it, if you are sending too many requests, they'll chop you off. They'll just stop you for a while, and all of that. Cost predictability and monitoring. You are spending money, right, to pay for these services. Is it worth it? Are you getting the value for that money that you're spending? Monitoring, privacy, security, audit, compliance in enterprise context. There are some situations where you need to be careful about the data that you are sending to LLMs because the LLM will not, especially the service providers, they keep everything or they store everything, right? So privacy is a key element. Then what else? You need to design for human in the loop and reliability. LLMs are not sufficiently um, reliable that we would take a human being out. It is a core principle that a human being must be there to validate the final decision. It's just like you saying you want to push to production, and LLM will do everything. There has to be a human being in the middle of it. Approvals, anything that requires, that is critical, right? There has to be a human in the middle. There has to be a human that at the end of the day has to approve it before it goes out. Otherwise, you can cause a lot of problems. There are some low criticality or non-critical things where, okay, you can just automate the whole thing end to end. But even at that point, there should be a human in monitoring and a human in notification. The human needs to be at least informed that this automated intelligence has deployed something, right? There always has to be a human in the loop. Then you have a UI UX aspect of it, which is how do you bring humans into the review process to review stuff that's going on, correction, feedback loops, and so on. Then you have failover. So remember, AI can fail sometimes. So how does your business process continue to function when you have fully automated it or when you have started becoming dependent on automation? What will happen if the AI fails? Do you have your rule-based logic or your knowledge-based or expert system that can at least fall back? Think of a chatbot. You wrote a chatbot and everybody's really loving that chatbot. And then all of a sudden, you know, um, ChatGPT goes down, you know, or Claude or whatever you are using as the backend for that chatbot. Do you have your rule-based logic that will say, okay, sorry, please, we are down, or it will just type and it, So you should always have some kind of backup plan. And this is a DevOps principle. There should always be redundancy. There should be a failover in case of any eventuality. Then you need to keep learning because AI, the technology is fast changing. Last year, we were talking about RAG. This year, we're talking agentic. 3 years ago, we're talking about LLMs. In 2020, 2021, 2022, we had 2020, 2018, we're talking transformers. 2020, we're talking large language models. By 2022, we're talking about OpenAI GPTs. We're now talking of generative pre-trained, right? 2021, 2022. In 2023, we're talking about large language models. We're talking about fine tuning. 2024, last year, we're talking about RAG. Today, we are nobody's talking about RAG, even though it's still there. We're talking about agentic AI agents. Next year, what we'll be talking about, if you have shut off your brain, you will not be able to catch up. So you have to be aware that things are moving fast and you need to move along with it. Track your model updates, API changes, deprecations, things will change. So your code base needs to be updated, to uh, track what's going on. Understand basic ML vocabulary, which is why I started off this particular class just going through the history of ML, talking about concepts. There's still a whole lot of other concepts, but over time we'll begin to get it. Understand the vocabulary, understand what these things mean, and you know how to use it. You should be able to talk to a machine learning engineer, right? As an AI engineer, you should be able to talk to a machine learning engineer to understand what they are discussing, and you should be able to understand what, or they should be able to understand what you are discussing. Benchmark compare tools. So always choose responsibly. Um, Remember to talk about safety in safety in AI is very key. We'll talk about that at some point. Now, because I'm running out of time, or basically I run out of time, I want to round it off quickly. So these are some of the concepts that you probably will need to know. You will face them. There are a whole lot of concepts, right? But we've already talked about large language model, LLM. A large language model is a neural network model that is trained on massive text corpora, a corpus of text that is gathered from, internet, from all sources, from everywhere, you know, and it reasons with natural language. So that's why it's called a large language model. It's a language model. It's trained for language. It's not trained for chess, for example, or for Go. It's trained for language. So it's a language model and it's very large. That's why it's called a large language model. Embedding is numeric vectors that represent meaning of text. It's basically language knowledge representation, right? So you use embeddings to, it's just numbers. It's just a vector of numbers, right? A sequence of numbers. So this sequence of numbers could be very long or could be very short. Some of them could be 256 floating point numbers. Some could be 1,000 floating point numbers. Some could be 32, numbers. Those 32 numbers, a particular sequence of numbers will represent one thing. Another particular sequence of numbers will represent something else, right? So you will not know the meaning. It's the AI models that know the meaning of these numbers. But you can always extract the meaning by writing code, asking the LLM or AI or model to tell you what that means to it. Because it's the embedding is not the meaning to you, it's a meaning to the model, right? So you use it for things like searching, clustering, similarity. So remember what I was talking about? I want to open an account versus, my account, I'm a new person. I would like to know how to, that similarity kind of checks. There are models that do that. Vision models for image are models that are meant for image classification, object detection. That's what they are designed for, and that's what they are trained for. And generation. Speech models are trained for transcription, translation, and synthesis. Then we have what we call multimodal models. The multimodal model is a model that has been trained on multiple um, media types or formats. So it can actually accept and produce different media types or formats. We call it modality. That's why it's multimodal. So it can be text, it can be image, it can be audio, it can be video, and a whole bunch of other things. Fine tuning is when you update a pre-trained model. A pre-trained model is a model that you've already trained with a lot of data. Typically, it takes a lot of compute for you to train a model. So for example, um, a typical model can take you 6 months or 1 year to train with 10 million to billions of data points. Most normal human, normal people or companies or individuals cannot achieve that. It requires a lot of money, power, and skill and compute, right? So most times you will not be able to train a model from scratch. Rather, what you do is you go and take a trained model or what we call a pre-trained model that has been trained to a certain point, and you fine-tune it. You add your own data, which will be less in quantity because you don't need to train everything. You just need to train it on some few things. So you get maybe 100,000, data points instead of a billion, right? Or maybe even a million in some cases, right? And then you can train it, you can fine tune. That's what is called fine tuning, because you're not really training the model, you're fine tuning it to become better. So a good example is there are models that speak English, but they don't understand the way African English is spoken, right? Language models. So you cannot take all of the recording voice data to train a language model from scratch to be able to understand the way Africans speak English. So what you could do is you take the one that's been already trained, and then you can get a less amount of data of recordings of speech by Africans, and then you can use it to fine tune rather, an existing language model, and it will be better able to understand and speak the way Africans speak English. So that's a good example. In fact, that's a project I wanted to do. I've seen a bunch of people have done that already. Then RAG, we already talked about RAG. RAG is retrieval augmented generation. So this is a way where you use a model, a language model in particular, to search over external data. So this data is not inherent in the model's knowledge, but it is data stored elsewhere, maybe in a database, what we call a vector database. So that database with the LLM can easily search and retrieve data that is stored in that database. Then you have function calling, like I said, or tool use, what we call tools. So you take an LLM and you allow it to be able to invoke external functions. So you give it additional capabilities that it doesn't have. And some of those capabilities are things that you yourself can write, right? Including functions in your code, API, code paths with structured output rather. Okay. Then we have agents and agentic workflow. So an agent is basically an autonomous AI. That AI, you achieve it basically by writing prompts, but they focus on specific workflows, and they are done in order to load workflows away from human beings where human intelligence will be required, but the agent can handle it because you have looped in an LLM into it. What do I mean by looping in? Essentially, you have prompts that you have written that go to an LLM. The LLM tells, is able to do stuff, make decisions and all of that, and send feedback back to your code. So that's agentic. If you want to know more about agentic, we have a track where you can also look at that. So other concepts, prompting and control concepts. So we have what we call prompt engineering. I hate that word engineering because, well, you are crafting prompts. You're not engineering it, but whatever. So I call it prompting. So crafting structured inputs, roles, constraints to control the model output. So that's what most people hear about, but that's not the biggest part of this whole thing, right? Then the system prompt, like I said, these are prompts that you, the developer, have added. You always attach it to whatever prompt the user sends, and you send it to the LLM. So it modifies the behavior of the model. Then you have what we call few shot or in context learning. Few shot is because typically, like I said, to learn, you require a lot of data, right? You require a lot of data. But when you use few shot, it means you can use much less data to train. So you use examples that you insert inside the prompt. Since the model already is smart enough to understand the prompt, instead of you retraining the model or fine tuning the model, you just put in um, additional data in your prompt or additional instructions that will, or examples that will help the model to do what you actually want it to do, right? Then we have what we call guardrails, safety layers. So these are additional filters and constraints that you put to prevent harmful behavior or harmful responses, off policy responses, or non-compliant outputs. So you're basically going to filter it. Hallucination is when a model gives you the wrong information with so much confidence that you yourself will believe it if you were not better informed, right? So sometimes it's due to wrong prompt, sometimes it's due to question being asked outside of the domain of knowledge of that model, and so on and so forth. Okay, then with scaling and deployment, inference is when you run a model, a trained model to get an output. Latency is the time it takes, basically. But those are some of the metrics that you use for an AI service. Latency is how long it takes before you get an answer once you've sent the prompt. Throughput is how much traffic the service can handle. Token cost is how much of the token capacity of the model is already taken, by system prompts and so on. Quantization, distillation, these are just ways to um, reduce the size of a model and therefore make it more usable without losing knowledge. You know, it's normally used for speeding up models so that you can install them on edge devices. And edge device are devices like phone and so on that don't have a lot of computing capacity, but you want to still deploy AI models in them. Self-hosted versus managed. A self-hosted is you are running in your own laptop or on a server, on your own server, while managed is the one that is run by the vendor. You don't have to deal with all those overheads. A vector database is a special database which you see the different types here, Pinecone, Weaviate, Quadrant, Chroma, that are used for similarity searching over embeddings. Typically, you just store embeddings in the vector database. So what happens is that when people ask a question, the LLM will generate an embedding, and then you now find an embedding that is close to, that's the similarity set, that's close to the embedding that comes from the LLM, and then you use that as to retrieve the solution. Sometimes you can map a solution to that embedding, and so it will pull out that solution. So that's why it's called retrieval augmented, because it really is to help with the retrieval of answers, that you have stored in that database. Other concepts, integration architecture concepts, orchestration frameworks. So tools like LangChain, Llama Index, Semantic Kernel allow you to manage multi-step AI workflows. We are going to talk about Lang and these others later, so I'm not going to dwell on it. Memory, you have short-term versus long-term. So like I said, there are mechanisms to persist session state across AI calls. Like I said, if you don't persist the session state, each time you send a prompt, it will not remember the previous conversation. So it will be like your grandma that has amnesia or doesn't remember what we discussed yesterday, that kind of thing. Evaluation is LLM evals. So basically, it's a method for you to test the capacity and knowledge metrics of how good the LLMs are. A hybrid stack is basically a stack that is made up of an AI, modern AI using LLMs, neural networks, plus classical machine learning approaches, including the rule-based, knowledge-based, and so on, to be able to get the best of both worlds. Enterprise risk concepts. So we have what we call P2 privacy controls, how you handle personal data as passing through LLMs and other AI systems. I just talked about that. Model risk and explainability. So there's something we call explainability, which is when a model gives you an answer, how did it arrive at that answer? That's explainability. I should be able to understand. It should be able, even the model should be able to explain to me how it arrived at that answer. But because most models are black boxes, neural networks are basically black boxes. You don't really know what goes on in there. Like I said, it's just a stack of floating point numbers that have been aligned in a specific way to store that memory. So it cannot even explain to you how it got. But there's a field where we are going to be looking at, okay, can can AI be able to explain, you know, how it came by this answer? So that's explainability. Um, Yeah, and explainability is important because if it fails, then we should know how it or why it failed or the failure modes. Then copyright and IP risk. So that's basically intellectual property, legal considerations. When outputs reproduce training data. So the whole idea is this: like you are training models on stuff. Some of those information you're training models on are intellectual property. So the question is, do you owe the owners of that intellectual property if the model regurgitates what you use to train it? It's not supposed to regurgitate what you use to train it. It's supposed to generalize and give you answers from its own self. But if it now becomes too similar to somebody's intellectual property, then there is a problem, or there could be a problem. So red teaming, safety testing, this is just how you stress test the AI. Um, to avoid harmful or non-compliant behavior. Okay, so on this, I had a bunch of different AI frameworks. So we have OpenAI, which everyone knows, GPT, Whisper, DALI, the Anthropic, Claude, then Google DeepMind, Gemini, Microsoft Azure has its own OpenAI hosted versions. Amazon Bedrock, XAI Grok, that's Elon Musk's company. Then you have open source model providers and inference platforms. So these are the open source ones. So you have Hugging Face. Hugging Face is focused on graphic image models and APIs, and then transformers as well. Mistral is efficient open models, but it has a paid API. Then Meta, which is a Facebook company, has Llama. So the whole Llama and Llama family comes from Meta. Then open source LLMs. Then we have Cerebras, Together.ai. Then of course we have these recent ones, DeepSeek and the rest of them. A lot of them are coming up now. So some of the vertical APIs that you also see, you have Vision APIs, Azure Vision, Google Vision, OpenAI GPT Vision, speech APIs, you have Whisper, Azure Speech, DeepGram, Assembly AI, Search, RAG and indexing, Pinecone, Weaviate, Elastic AI Search. These are just basically search algorithms and the similarity matching when you are implementing RAGs. Then function calling and agents. So you have OpenAI assistants, you have LangChain, which we already talked about, agents. So you can build agents with all of these kinds of frameworks. Then you have safety and guardrails. So you have Microsoft Safety Content Safety, Nemo Guardrails, Llama Guard, and so on. Developer frameworks and SDKs you can use as a developer to integrate to this AI. So you have orchestration frameworks like LangChain, Llama Index, Haystack. You have SDKs. All of these guys have SDKs, OpenAI, Python, or JavaScript AI SDK. Anthropic SDK, Google also has its own SDK. Then in JavaScript apps, you have Vessel, Next.js. I'm sure even mobile apps would have it as well. Flutter, Android, and so on. Then you have server deployment stack. So NVIDIA has Triton, you have VLLM, TGI, Olama. Olama allows you to install a whole bunch of different models on your backend. So you can then write APIs around it. Then you have enterprise AI platforms. You have Azure ML, GCP Vertex, AWS SageMaker. These are basically like services you just pay for and you use. You don't need to worry about configuring or setting up yourself. But it's still good to learn how to do these things in case you get a job that says, oh, set this up for me. Databricks, Mosaic AI, Snowflake Cortex, IBM Watson. I talked about IBM Watson, the thing I used, years ago. That was even before all of these LLMs came to being. Um, yeah, then specialty, Code AI, GitHub Copilot will allow you to do autocomplete, really speed up your coding. We are going to look at these ones maybe next week. Amazon Code Whisperer, Cursor. Cursor is basically an IDE that is just AI. It uses VS Code library, the VS Code IDE library, and then it adds all kinds of intelligence into it. You have this for legal and contract AI, Harvey, Ironclad, Lexicon, healthcare. You have Google MedLM, DeepMind, MedPalm, robotics, NVIDIA Jetson. Jetson is actually a small system, SoC system on a chip that has a GPU, Jetson a GPU. Then Luxon ISE, HU, finance and trading. You have Bloomberg GPT APIs and Quant AI tools. So these are some of the emergent fields in AI and ML. So you have ML ops. All of these are this ops, that ops, ML ops, productionizing ML training and deployment. AI ops is using AI to automate IT and SRE tasks. LLM ops and Gen AI ops is running LLM applications safely and at scale. Data ops is reliable and governed data pipelines. So now data pipelines is very important, especially for training of all of these models. Then we have model ops, enterprise governance across all model types. Prompt ops, controlled lifecycle of prompts. RAG ops, production reliability of retrieval-based LLM systems. Edge AI ops, running AI on devices, not on clouds. And then AI sec. So this is security and securing your AI. Okay, so this is my last slide and the answer to the question. Somebody asked, what's the difference between an AI engineer and an ML engineer? So this slide tells all of that. So right now, I believe it's very clear. An ML engineer is the engineer that trains the models. So the ML engineer is going to be deeply involved in the statistical and algorithmic aspects, training the models, writing the training programs, data pipeline, management, designing the models, parameter hyper tuning, hyperparameter tuning, and just basically training models, designing models, building them, scaling them, all of that. They deal with models, data preprocessing, feature engineering, model optimization, experimenting with different algorithms and hyperparameters, fine-tuning, tuning hyperparameters, accuracy, even the distillation, the quantization and all of that, right? That's what ML is focused on the model that is smart, working with the research side of AI and developing proprietary models. That's ML engineer. AI engineer is what those of you on this call will be. Your own is using the models that the ML engineer does to bring intelligence into products, into larger systems, right? So a broader role of designing and deploying complete AI applications that use models, which often include the ML as a component. So your task would include integrating machine learning models into larger systems, voice assistants, chatbots, smart devices, smart applications, smart websites, building and deploying robust APIs. So for those who want to do it on the back end, you bring those models, you encapsulate it with an API, and then you deploy those APIs, and they become available for people who need to access those models via APIs, ensuring that the AI systems will scale reliably and integrate with existing business processes. So you already have existing business processes. How do you build your AI, or how do you bring these AI services and capabilities into these business processes? And so an AI engineer will often work with pre-trained foundation models. So you're not going to train models on your own. You use pre-trained models. You can fine-tune them with data, right? Or you can enhance them with things like RAGs, with prompt uh, tuning, prompt, cleaning of data, customizing of prompts, and so on. So that is the difference between an AI engineer and an ML engineer. And that is also the end of this class. Thank you very much. Any questions? I think I will stop the recording. There are some people who ask that, okay, maybe we should have questions in the recording. The recording looks like it's going to be long, so I don't know. Go ahead, Larawaj.
Thank you very much, sir, for the time and the deliveries. My question is actually personal, but my direct question, sir, is that as you have just given us the very last distinction between an AI engineer and ML engineer, if I may ask, in this training, like I have told you, sir, like I mentioned earlier, I'm enrolled in the agentic AI, but I chose to go to the ML because I know I'll benefit in it very well. But then coming to this class, I just came around and it seems to me that AI engineering is more about this course than machine learning. I don't know if I'm right in that. So if you are like someone that wants to be an AI engineer, would you rather that he comes to this class or be in machine learning as a second leg of his training, like me, sir?
I didn't get the last thing. You said AI engineer is
Yeah,
what?
AI engineering, yes.
You
Like
say it's
I,
this course. I didn't get
or,
that.
or machine learning core track.
Yeah, so to be honest with you, it's really your choice. There is huge value in both sides. It's just like saying, I don't even know what, should I be the cook in the kitchen in a restaurant, or should I be the waiter that brings the food from the kitchen to the customer sitting at the table? So the ML engineer is going with that analogy, is more like the person that is cooking the food in the kitchen, building the models, while you are bringing or not you, well, the AI engineer is the waiter that goes and brings the food from the kitchen to the customers. You are bringing the capabilities of these models to products that people actually use. People don't will not use the models as they are, right? People will use the products that leverage on the capability of these models. So, for example, ChatGPT uses GPT. GPT is a model. On its own, you could not do anything with it. But the interface, that chatting interface that you interact with, somebody built it. The person that built that interface is the AI engineer, while the person that is training the ChatGPT model is the ML engineer. Both of them are equally important. They are both equally important because if the cook doesn't cook, there's nothing that the waiter will serve. And if the waiter doesn't serve, there's nothing, the food will just be there and nobody will eat it or enjoy it. And therefore, after some time, there won't be any money to run that business. So I think it's more about deciding what is your own passion. And if you cannot decide, well, I don't know what I'll tell you, but I think you were there in the other class and you were here. So you have heard both sides. I think it should be enough for you to decide. If you're more of a developer, you want to write code, you want to build products, then you are an AI engineer. But if you're more of a scientist, well, not really a scientist, you're still an engineer. I want to build models. I want to train them. I want to improve the capacity and capability of models. Then you choose ML engineer. So, but let me also tell you, if you are choosing ML, you have to know mathematics. So maybe that's going to be a tiebreaker for you or a deal breaker. If you're not really good at maths, that will be
Yes,
hard for you. Okay,
yes,
so
thanks so much. On the last
yeah,
note, sir, if I can add this bias to it, sir. I the reason why I'm in this training is to see how I can, on one side, use AI to enhance my work. I'm an engineer and in the telecommunication sector. So I'm looking at how AI will transform the telecom sector. And I want to be at the forefront of such a transformation. While on the other side, I know there could be some other areas maybe like healthcare. So I want to be a generalist and then a specialist in telecom. So
yeah,
that's why
that's still okay. So you have to do one at a time. So you choose which one you want to start with, right? Or well, if you want to do the two, I don't advise it. But if you have the capacity,
I've decided to in fact this course I never knew I would stay like this. Because what I'm seeing here is more of AI engineering. That's why I feel like maybe I should leave machine learning core and rather combine this with my identity AI. But I would go with me.
sleep over it, think about it.
Thank you
But
very
you
much, sir.
have to decide for yourself. My own is to help you achieve what you want to achieve,
Thank
but
you
you
very
have
much.
to decide. All right. Is there any other question? Okay. If there's no other question, I'll stop the recording now. Thank you very much. I I really